Swayam Prabha. Digital India. Educated India.
Phenomenon is called agglutination. So you see this East, Ata, Isi, and Ko, Han, all these are glued together to create a long string. And since English is not so much agglutinative, it has to resort to many different words to convey the meaning. And the extreme of no agglutination, it's called isolated languages. The example of that is Chinese. Okay, and Chinese really has to use many morphemes to express a particular meaning. And an example of agglutination and no agglutination close to our own languages, close at hand, is example of Marathi and Hindi, for example. Okay, Ram Ko, in Hindi, Ram and Ko will be written separately. This is called isolating behavior. In Marathi, it will be Rama La, and Ram and Ala are glued together. So this is an agglutinating behavior. So languages fall in different places between the two extremes, isolating languages and agglutinative languages. And whenever you see morphemes joining together, you know that agglutination is happening. So that way, going, okay, going is an example of agglutinating behavior. Okay, English is not an agglutinating language. It has an agglutinating behavior. Go and ing are being joined together. Okay, so now confusional divergence we saw French vomir becoming to be sick. So 1 word to 3 word mapping. English stab becoming chure se marna in Hindi. So 1 word to 3 word mapping. Categorical divergence we saw change in the part of speech category. So the play is on is preposition. Khel chal raha hai. Chal raha hai is equivalent of on. Okay, chal raha, and is equivalent to hai. So on is chal raha. So there is this preposition getting converted to chal, which is a verb, raha, which is also a verb. Okay, so this is an example of part of speech divergence. Then SVO, SOV is very common. The verb comes in the middle for English, German, French, many such languages. They're called SVO languages. And Hindi is SOV, Bengali is SOV. Almost all Indian languages are SOV, except for Khasi, which puts the verb in the middle in English. There is the other behavior, which is VSO, which is verb coming in the front of the language. So Arabic is an excellent example of VSO, where the verb comes in the beginning of the sentence. It is a very interesting fact that there is no instance of any language in the world which is which puts object before the subject. There is no language. Okay, you have SVO, you have SOV, but everywhere the object is coming after the subject. So there is no language where you have where you have OVS, okay, or OSV or VOS. No, you don't have. That's an interesting thing, and why this happens is something we can ponder about. Now SOV is Peter plays basketball, play in the middle, Peter basketball khelta hai in the end. Head swapping divergence is the swapping between head and modifier, head and dependent, head and modifier. You have done dependency parsing. So here head swapping is the swapping between head and modifier. So Prime Minister of India, Prime Minister of India, uh, Prime Minister in India, they transpose their position. Okay, so Bharat ke Pradhan Mantri. Pradhan Mantri has gone after K and India has come before K as Bharat. So this is called head swapping divergence. Just think about which is the head and which is the dependent or modifier, and are they getting interchanged. It's called head swapping. Then constituent order divergence. Singh, the Prime Minister of India, will address the nation today. Bharat ke Pradhan Mantri Singh. So here the constituent order, you have done constituency parsing, so you would know what are constituents. The PM of India is a chunk, okay, or a small phrase, and that comes as the qualifier for Singh, and that gets swapped with Singh now, Bharat ke Pradhan Mantri Singh. So there is a slight difference between head swapping divergence and constituent order divergence. Okay, not all constituents are dependent on each other, but the constituent can change its position, should change its position depending on the demand of the language. Adjunction divergence, she will visit here in the summer. वो यहाँ गर्मी में आएगी. So here the adjunct adjunct is in the summer. Okay, the difference between adjunct and argument has been explained before. The essential noun phrases are arguments. The non-essential ones which bring in additional information are called adjuncts. Now, head swapping, constituent order, adjunct divergence. These three divergences, they look very similar. Okay, they are almost identical. So head swapping, constituent, adjunction. These three are almost, under the same type, I would say. But there are subtle differences between them, which you should be clear about. Okay, adjunction divergence is purely the additional information bearing phrases getting different positions. So she will visit here in the summer. There is no way in Indian languages you can keep in the summer at the end. In the summer has to come to the front or a position which is near the front. Preposition stranding divergence is a very peculiar phenomenon of English. I don't know of any other languages which allow this. Who do you want to go with? So the sentence is with whom do you want to go? किसके साथ आप जाना चाहते हो? So go with whom? With whom, and see the amount of distance with has traveled. So there is a peculiar phenomenon in English. It is called preposition stranding. With whom has become whom do you want to go with? Who or whom both will work here. So the preposition gets separated from the noun by a long distance. So this is called preposition stranding. So this was a hurried look at the divergence, and it is the divergence which makes the translation process difficult. There are both lexical semantic, which depends on the words and phrases, and structural, which depends on the order of words and phrases, which creates the difference between the two languages. Now, this naturally gives rise to a discussion on what is called Vokwa triangle. Okay, this has really been the ruling conceptual structure for machine translation. So, okay, so let me illustrate this with an example. John eats bread. This is the SVO structure. John, main verb, eats bread, subject, object, verb. We know that to translate this to Hindi, we'll have to apply the transformation SVO to SOV. V should go at the end. So I can do this quite easily if I have the constituency parse structure available to me. So I have S, NP, VP. NP goes to N and John. VP goes to V and NP. This NP actually goes to N and P, proper noun. VP goes to V and P. V is eats, NP, N and bread. That is eats bread. Now, if I have the parse tree, I apply a simple inversion rule to invert the NP and the V, those positions. So NP comes in the beginning. John bread eats. Now substitute the word John bread khata hai, and you are done. Okay. So this particular transformation, it required what is called a bit of analysis on the source sentence. We had to go from the raw input to at least the parse tree. So this is the analysis. This is the analysis stage. And after getting this analyzed form, we apply transformation rule on this. Okay, so this is what is expressed by Vokwa triangle. The Vokwa triangle has the left axis, left line as the analysis line, and the right line as the generation line, and the horizontal line is linking the two. The analysis is on the left, generation is on the right. Now what we did just now was that we went from graphemic level. Graphemic means the raw words level. Okay. From there we went to the syntagmatic level, where there is a syntactic analysis done on the sentence. And then we transited to the other language side by a transfer, syntactic transfer. We inverted verb and noun phrase positions. So that is called the transfer. And then from there we can generate the target Hindi sentence. John bread eats, John bread khata hai. And the analysis was producing the syntactic tree. Now this analysis level can be from very simple to very sophisticated to the tip of the Vauquois triangle, where it goes to completely disambiguated form, and that is a deep understanding level. All the words are disambiguated. All kinds of structural ambiguities have been resolved. Okay, I saw the boy with a telescope. Who has the telescope? That ambiguity is not there anymore. Okay, somebody's microphone is unmuted. Okay, everybody please mute your mic. There is an echo. So at the deep understanding level, all ambiguities have been resolved. So all ambiguities have been resolved. So this is hard work. It requires full natural language processing to be applied to the raw input. And from there, we begin to produce the sentences of the target language. So now this is called transfer. Going from left-hand side of the triangle to the right-hand side is called transfer. So that's why this is called the ATG framework: analysis, transfer, generation. So Jyotsna, kindly add this term ATG, analysis, transfer, generation framework. Okay. So analysis is on the left hand side, transfer is going from left side to right side, and G is generating the target language sentence. ATG, this is called. And in the deep understanding level, all ambiguities have been resolved. Now you see there are many different kinds of transfer, many different levels. You can see this is the most elaborate form of Vauquois triangle. Vauquois, by the way, was a French physicist. Okay, and in the early days of AI machine translation, people from different fields have contributed. They have entered AI and have contributed, even computer science, I would say. And this is an example of a physicist coming into machine translation and contributing. Another nice example is Hopfield-Net. Hopfield-Net is a model of neural computation which is recurrent, and there the main discussion is the stability of the Hopfield-Net. Hopfield himself was a physicist, so he used what is called the spin theory to create a model of neural network based on spin theory. Now look at the different levels on the left-hand side of Vauquois triangle. We should always keep Vauquois triangle in mind to be very, to be very sure at what level are we operating for machine translation. How much is the analysis we require? So if the languages are very close to each other, if the source and target language, let's say Assamese Bengali, Spanish Catalan, okay, French English even. So if I take an English sentence and I want to translate to French, I will go some distance up. Okay, I'll do some analysis. So one analysis could be I get the chunk of adjective and verb and adjective and noun, and do a transfer by inverting noun and adjective, because in French the adjective goes after the noun, and then generate the French sentence. Okay, by substituting words. So this is showing that here the analysis is of some small amount, and then I can begin to generate the French sentence. But if I'm translating from English to, let's say, Arabic, where I need lot of analysis to go to a level from where transfer will be possible. So in particular, in Arabic, the sentence begins with the verb. So I'll have to arrange to put the verb in the beginning if the English sentence is the input. Okay, so I have to bring the verb to the front. So that kind of constituency adjustment will be required. Then Arabic is very agglutinative, so I'll have to break the word into its small morphemes and have the equivalent English words arranged. So no, in this case, this will be different. Of course, I'm going from English to Arabic, so I'll have to glue together the English words. Okay, for example, to Ram will have to become Ram Ko. So I'll have to arrange to add Ram and Ko if I'm doing Marathi, for example. So agglutination will have to be arranged, okay, during transfer, and then we produce the Arabic sentence here. So the point I'm trying to make here is that the source language and the target language decide how much analysis is required before transferring to the other side and then begin generating. So it is almost never the case that you have to do all disambiguation. Okay, you have to do all disambiguation. Almost never the case. In particular, if the languages are very close to each other, for example, Assamese and Bengali, the word chuti means holiday. Okay, so our Diwali holidays are coming, for example. Chuti is used in Assamese also, so I don't have to transfer chuti. Okay, I just and in fact Assamese and Bengali scripts are also same, almost same. Okay, there are only two letters which differ. So I apply cha, u, and ta and e, and I get the Assamese word chuti. Okay, so Amar chuti chai. I want leave. So that is almost word to word substitution in Assamese, and I don't require so much analysis to be done. I can almost be at the base of the backward triangle and begin transferring from the base. Okay, from the base to Assamese. Catalan, Spanish also same. So I don't need so much of analysis. So if it is insisted on that you do go to the tip of the backward triangle, we'll find that, well, so much of investment after all was not necessary, and therefore this interlingua or deep understanding level was not necessary. That is why interlingua based machine translation, though, is an idealization and extremely useful thing to do, because from the deep understanding representation you can do many things: question answering, summarization, many things. So if you go to the deep understanding level, not only are you benefiting the machine translation task, you are also benefiting many other NLP tasks. But for the task at hand, which is immediate need, I don't need so much to do. Okay, so that's why we have transfer-based machine translation. Now let's look at the levels. Grapheme level is raw sentence. Morphosyntactic level, I do morphology analysis. Syntagmatic level, parse trees are constructed. Syntactico-functional level, parse tree, both constituency and dependency are created. Mixed levels, there is a little bit of semantics also comes in. Semantic roles, for example. Logico-semantic level, I convert the sentence into some logical form, predicate calculus, for example. Interlingua level is very close to deep representation, except that all ambiguities are still not resolved. For example, pragmatic ambiguities are not resolved. In deep understanding level, everything is resolved. And look at the generation side. The final product is the text. Okay, before that you have tag text. Before that you have C structure, conceptual structures, constituency structure. Before that, functional structure, that is dependency structure. Multi-level description, semantic roles, dependencies, everything. Then predicate arguments would be the predicate calculus based representation. Semantico-linguistic interlingua. Here you have maybe some kind of social factors also coming in. Ontological interlingua is independent of any language. This is a very rich knowledge structure which is used. Now, depending on where you are, so if you are working at the level of F structure, that is dependency relations, then you need syntactic transfer of a deep kind. Syntactic transfer of surface kind is transfer between C structures. You just invert the verb and noun phrase, for example. So this was a very nice conceptualization of machine translation back in 1960s. So even though you are doing machine learning, deep learning, and so on, just keep noticing where the insights came. The insights came long before, really. Okay, long before. And necessity is the mother of invention. There was not much data. So what could a person do? If I do not have data, what do? I just think about the problem. Okay, I just think about the problem and try to understand what are the nuances, what are the constraints, and so on. Okay, so those who do not have resources and data, or situations where resources and data have not been created or are not easily available, we have to become innovative and we have to become creative in our problem solving approach. Okay, साधन नहीं है तो क्या करना है? We have to look inside my brain and see how much of juice I can extract from my own brain, from my own thinking about the problem. Okay, so this is a very nice example of a theoretician thinking about a concrete problem, the problem of machine translation. Okay, which was thought to be easy at the time. People thought it is trivial to translate from one language to another. But here was a person, Wakwa, who sat down and uncovered layer after layer after layer of complexity of the task. Okay, this is the lesson to be learned. So Wakwa triangle is a nice framework for understanding machine translation. So far, so good. Are you seeing the Wakwa triangle on the screen? Somebody verify?
Yes, sir. Yes, sir.
And also you heard what I said. When you don't have data, you have to think. Did you hear it?
Yes, sir.
Yeah. Okay. So, okay. Now there is this universality hypothesis, which says that at the level of deep meaning, all texts are the same, whatever with the language. So universality hypothesis has a grand goal to unify all languages into one single framework. Not at all a recent thing. It is there since 1960s, 70s. Okay, and in fact, in 1992, we got this project from United Nations, Universal Networking Language. There at IIT Bombay with 15 countries participating in the project, and that was also based on this universality hypothesis. But the practical situation demands that maybe this hypothesis is really the idealization. It can remain at the background. We can worship this hypothesis, but in practice, maybe we don't need so much disambiguation after all. Now, understanding the analysis transfer generation over Wakwa triangle, the ATG framework. So I have this sentence: सरकार ने चुनावों के बाद मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. सरकार ने चुनावों के बाद मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. So this is the Hindi sentence, and look at the notational convention also. H is the Hindi language, T is the transliteration, G is the gloss, E is the English sentence. So for any non-English text, you have to represent the text in these four forms. If you're writing Romanian, Hungarian, some language from Africa, these four forms are mandatory. The original language and its first letter, T for transliteration, G for the gloss, and E for the target language's first letter. Okay, so if I'm translating from Marathi Bengali, I'll have M, T, G, and B. Now, what is transliteration? I am writing the Devanagari characters or non-Roman characters in Roman characters. सरकार ने चुनावों के बाद मुंबई में करों के माध्यम से अपने राजस्व को बढ़ाया. Now, transliteration you can see is again non-standard. People write transliterated text in their own way. Okay, सरकार ने, I somehow have put capital S here, though that is not required. We should put small s there. Sarkar, somebody will write double A, another person will write small a, one single A. Somebody might write a capital A to indicate A ki matra. So Rajaswa, somebody will write V here, somebody else will write W here. So transliteration therefore again becomes challenging because the standardization is not very strictly followed there. Now comes gloss. What is gloss? Gloss is word-to-word positional correspondence. Sarkar ne. Sarkar is government. Sarkar is government. Ne is the ergative marker, okay, which Hindi uses for past tense, transitive verb, and agent. Chunao is elections. Ke baad is after. Mumbai. May is in. Karo is taxes. के माध्यम से is through. It's अपने, it's राजस्व revenue. को is accusative marker. बढ़ाया increased. So this is the word-to-word substitution, word-to-word or phrase-to-phrase substitution, not necessarily one-to-one. Okay, के माध्यम से has become a single word. This is 3-to-1. We have seen example of 1-to-3, stab. Okay, so this conflation deflation can happen over two languages. And then now I rearrange the gloss. The government increased its revenue after the elections through taxes in Mumbai. The had to be inserted and we had to rearrange the words. Okay, so this is an example of Hindi to English going through transliteration gloss, not computationally, but for communication purpose, writing purposes. Now, interlingual representation actually requires complete disambiguation. If I have a sentence like Washington voted Washington to power, so vote is the main verb. The at past indicates past tense verb. This is an action, so vote is not a noun, it is a verb here. So I have the tag here is an action. The object of voting is Washington, and Washington voted Washington to power. Goal is to power. Agent is Washington. So this Washington is the city of Washington. And the second Washington is the US President Washington. Emphasis is placed here for some reason. Washington voted Washington to power. Okay, let's see. And power is a capability. Washington is a place. Washington here is a person. So all disambiguation is done by means of these kind of flags. They are called speech acts. And the words are disambiguated by means of these easy linking. Here vote is an action, power is a capability, not electric power, okay, but power in the sense of capability. So it requires complete disambiguation. Now the kinds of disambiguation which are needed for complete and correct interlingua graph are name disambiguation, part of speech disambiguation, attachment disambiguation, sense disambiguation, co-reference disambiguation, semantic role disambiguation. So here are some examples. Sentence: I went with my friend John to the bank to withdraw some money, but was disappointed to find it closed. I went with my friend John to the bank to withdraw some money, but was disappointed to find it closed. So bank, the circles are not properly placed. Bank is noun or verb. So this is part of speech. Then John is the name of a person. So this is named entity recognition. The circle should have been on John. This is named entity or proper noun disambiguation. Then financial bank or river bank. This is the sense disambiguation, WSD. Okay. Then I have co-reference resolution. So John went to the bank to withdraw some money, but was disappointed to find it. The circle should be on it. I should correct this. It is a pronoun. Now it refers to which noun here? Okay, it can refer to money, it can refer to bank, not to John because John is a person type noun. I, no, pronoun. Friend, no, pronoun. Friend is typically he or she. Okay, so what does it refer to? It has two choices, bank or money. Now we have to do the correct disambiguation of co-reference. This is called co-reference resolution, binding the pronoun to the correct noun. And then there is a subject drop disambiguation. So you see this is a much more complex phenomenon and not much progress has happened in this area. The ellipsis, this is so-called ellipsis problem. I went with my friend John to the bank to withdraw some money, but was disappointed to find it closed. Who was disappointed? Okay. I went with my friend John. Who was disappointed? Was it me or John? So was disappointed to find it closed here because of the syntactic structure of the language. We'll propose that here the pro drop. This is called pro drop. Some element has been dropped here, so it should be I. I was disappointed. So all these processing has to be done, and all this disambiguation is necessary before the interlingua is obtained. Now, in the early days of machine translation, this kind of analysis used to happen on source sentences. Now, of course, everything is either statistical machine translation or deep learning based system. But remember that if you don't have data, you cannot do those. You cannot adopt those practices. Okay, you will have to make use of rule-based system. But again, you will object. So if there is no data, do they have those basic NLP machinery? Do they have a POS tagger? Do they have a named entity recognizer, dependency parser, things like WordNet, Universal Dictionary? Do they have all those? No, that is also a very important challenge. So languages indeed are at different levels of advantage and disadvantage. There are really very, very poor resource languages. If I take, let's say, Swahili as a language, where of course a lot of NLP work has happened, linguistic work has happened. Okay, people have tried to understand the property of the language, but resources and tools, not much. Okay, English that way is extremely resource and tool rich. But is that tool and resource sufficient to solve all NLP problems of English? Not really. Okay, otherwise, why would English use so much of machine learning and so much of data? What about Hindi? Hindi is moderately resourced. German, French, less than English, but not so much as English. Okay, English by some luck has gone through a very well planned path of development. By some stroke of luck, by some concatenation of circumstances, as the phrase goes. But other languages have not been so fortunate. I know of languages where people straight away started working on machine translation. That was not the time when data was available. They started straight working on machine translation, not really caring to develop the basic resources, part of speech tagger, morphology analyzer, and so on. And where did that land? Money was spent, a lot of papers, etc., got produced, but the ground level resources which are required for further development, ground level infrastructure, which is required for further NLP work, that did not get created. Okay, so we need dependency parsing, we need part of speech tagger, morphology analyzer, we need lexical resources like WordNet. So IIT Bombay has contributed a lot in this particular space, the WordNet. We were the first to create Hindi WordNet and then link it with other Indian languages also. So you either have a lot of data, or you should have NLP tools and resources, which enables you to give transfer rules from one language to another. Which one is easier, to get data and run deep learning without doing anything? That doesn't really work. Even if you have got a lot of data, for agglutinative languages which have a lot of complexity in syntax and morphology, just feeding data into a machine learning model doesn't work really. Okay, you need to understand the properties of the language. So here is the system architecture for us, where we build a system for English in the machine translation system. And Marathi has always been also an important language. So English, Hindi, Marathi, we have worked a lot on machine translation involving these three languages. So named entity recognition, Stanford dependency parser is used, clause marking is done, word sense disambiguator, we have our own system for this. Then the sentence gets simplified into small text segments. This is the text simplifier, and then you can merge these also. And the simple sentences are analyzed through parsing, feature generation, attribute generation, relation generation. Okay, feature, attribute, relation, all these things are generated for the words, and relations are also found out. So they produce a semantic graph From that semantic graph, we produce individual Hindi sentences and then merge them together. So that used to be a framework some 10-15 years back. The target sentence is generated by applying lexical transfer, that is word and phrase translation. Morphology synthesis, you take the word jana and convert it to jaunga, that is the morphological transformation. And you take mai and jaunga, put them in proper syntactic order, mai and jaunga. So these three are fundamental steps in generating the target language sentence: lexical transfer, morphological synthesis, and this is called syntax planning. These are the basic steps in generation. So the generation architecture is also shown here. This is from one of our papers for English in the machine translation in agricultural domain, okay, quite some time back. And you see the pipeline here. There is UNL parsing. The UNL graph is given. That means the semantic graph is given. So the parsing is done on the graph. Graph is in the form of a textual predicates. And then if any error is to be corrected, this is done. Then lexeme selection. So you have vote as a kind of activity. Okay. Then the correct Hindi word for that is taken. Okay. Then case identification. Should it be object or agent or instrument or beneficiary? Then if it is case marking is properly understood, then you generate the morphology. Okay, is it Ramko or Ramne or Ramdwara or Ramse? So this is the morphology generation. Then function word insertion, you produce the function words like per, okay, ne, etc. So morphology and function word go together. Syntax planning is you finally place the Hindi words in proper order. Okay, Ram se yah kaam nahi hoga. So Ram se yah kaam nahi hoga, properly ordered sentence. And this whole pipeline of process actually requires UNL repair rules, UNL to Hindi dictionary. So there is a universal dictionary where there are no language words, but there are only concepts. Okay, so think like a bank as a kind of financial institution that is converted to Hindi bank, ba, aikar, bindi, and ka. Then UNL relation case, relation to Hindi case mapping. There are noun rules for morphology, verb rules, adjective rules, function word insertion rules. There is a priority matrix which controls the relation priorities. That means if it's an agent, if between two nouns, which one should I place first? The noun which is the agent, that should come first. Ram ne sham ko dekha. So the Hindi canonical order is first subject, then object, then verb. So Ram ne should come first, Ram ko should come second, and dekha. So all this is done by means of rules. Okay, everything is in terms of rules. So we have sat down and really fortunate to have English tools and resources, Stanford, NLTK, etc., etc. Make use of those and then apply various transformation, which was our own, and then produce the Hindi sentence. So that was our interlingua-based machine translation system. The transfer-based machine translation system, our role was Marathi and Hindi. So this was again a nationwide project. This is called the Indian language to Indian language machine translation project. Many different institutes worked together about 10 years back, and they created systems for 9 Indian languages. Our task was to build the translation system between Marathi and Hindi. Marathi, Hindi, Hindi, Marathi, both. And we developed both rule-based and statistical approaches. So that is when slowly the statistical MT was making its appearance. So the architecture is again very simple. You take the source sentence, go through morphology analysis, part of speech tagging. So morphology analysis, jaunga is broken into jana and unga. Part of speech tagging, chunking, vibhakti computation, named entity recognition, words and disambiguation. After that, you transfer to the other side, Marathi. Lexical transfer, Larka becomes Mulga. Agreement features, so Ram ko becomes Rama La. Intra-chunk, group the words. Okay, group the words. If Hindi has words separated in the chunk, maybe Marathi joins all together because inter-chunk. So between chunks, establish the relations. Okay, Ram ne Shamko, Ramani, Shamala. Okay, so now establish a relationship of Ramani and Shamala to the main verb. Main verb is dekha, and then you generate the words, get the target text. Okay, so this is a very intuitive, well understood pipeline, but huge amount of complexity at every box. Morphology analyzer for Marathi, Hungarian, Arabic is not easy to do. They are mainly done through finite state machines. Okay, these days people apply machine learning also. So the Marathi Hindi system was also evaluated. Now evaluation itself is also a big task in machine translation. So typically human manual evaluation has these 5 levels. Score of 5, correct translation. Score of 4 is understandable with minor errors. Score of 3 is understandable with major errors. Score of 2 is not understandable. Score 1 is completely nonsense translation. Now that we have been working with machine translation for several years now, we have seen all kinds of output from the machine. Okay, extremely correct, extremely nice correct translation to completely nonsense translation also. And the accuracy measure is typically, reward S5, score of 5 very heavily. So 1 into S5, 0.8 into S4 plus 0.6 into S3, and give no credit for sentences which are at the level of not understandable and completely nonsense, and divide it by the total number of sentences. Then you get some kind of accuracy score. This is different from what is called blue score. Okay, blue score is different. Blue score is completely automated evaluation. This evaluation is manual. Now we did calculate the accuracy of different modules. Word generator, for example, had an accuracy of about recall of about 0.9. Precision was lower. Precision was less than 0.8 in the word generator module. So each module, part of speech tagging, morphology analysis module, Vibhakti computation. Vibhakti computation is case marking, words and disambiguation. Everywhere we did precision and recall computation, and this was for a specific domain. So the evaluation was on 500 web sentences. The evaluating body gave us 500 web sentences and asked us, tell us what is your accuracy. So we got about 65.32 at that point of time. Now the accuracy is much higher, because Marathi and Hindi are closed languages. If you have a lot of data, then you can really arrange for high quality translation. And we have now about more than 1.5 lakh parallel sentences. Now I come to statistical machine translation, which was there since 90s. It was born in IBM. It first tackled the main problem of alignment, word alignment problem. So the statistical machine translation is really quite intuitive, and human beings seem to be doing that kind of translation in their head. So I give you this parallel corpora. Nesu is I carry, ponese he will carry, nesse he carries, nesso they carry, yedu I drive, plavo they swim. I think this is Czech. So Czech to English parallel corpus is given to you. Now if you look at the parallel corpus for some time, you will be able to translate new Czech words or phrases. Okay, so just notice this. Nesu, ponese, nese, neso. Everywhere the common substring is nes. And on the English side, you have carry everywhere. I carry, he will carry, he carries, they carry. So I think you can possibly see that nes and carry have something to do with each other, right? And yedu is drive and plavao is swim. Now yedu, nesu, if you compare, in both cases, u is the common morpheme and I is the common pronoun. So you can begin to think that, well, there is some correspondence between u and I. He will carry, what does he correspond to? Okay, it is like puzzle solving. You try to find out the morpheme to morpheme correspondence. He corresponds to what? Let me see. I have ponese here and he carries nesse here. E is common between the two strings. So most probably he corresponds to the morpheme E. Now Nesau and Plavau, OU I see at the end of the string. So, and I also see they pronoun as common. So maybe OU has something to do with they. Okay. And yet is drive most likely. And U is corresponding to I. So in the mind, we can keep breaking the words or sentences into their parts and begin establishing correspondences. This very activity is called alignment. Okay, this is called alignment. So this activity of establishing correspondences between morphemes is called alignment, and we are mentally doing this alignment. I can also use this alignment knowledge for new sentences. I will carry. Okay, I will carry. How do I translate this? I go back to my parallel corpus and look for evidence of I. I seems to be U. Okay, I carry and I drive. U is the common morpheme, so I keep U in my hypothesis space. Will corresponds to what? Will, I see Ponese, he will carry. That is the only word. And he, I thought is E. Ness corresponds to carry. So Po must be for will. So I also keep Po in my hypothesis space. So I got Po, I got U, and then carry. Carry is Ness. So I have three elements: U, Po, and Ness. U, Po, and Ness. So I will carry. Now I'll have to arrange. I have these three morphemes. Now I have to do syntax planning. Have to arrange them properly and put them together. So I will carry. Will should become Po ne su. Po for will, Nes for carry, and U for I. Okay. So see now what has happened. I will carry. I comes in the beginning of the sentence, but in Czech, the I morpheme, the corresponding I morpheme goes to the end of the string. Also notice the agglutination. Czech is agglutinated, so I will carry three words have been glued together to produce ponesu, and this is a glued string. Po has come to the beginning, so the auxiliary verb will has come to the beginning, and will carry is po-ness. Okay, so Po and Ness is will carry, and that is like English. First auxiliary, then the main verb. Okay, and then U is I. So I can easily create the Czech sentence. So while you are doing this, you should see mentally what you are doing and do the machine translators, mechanical translators today. Do they go through similar kind of? A lot of similar between human beings do in components of the word. They drive. What will they drive translate to? What will they drive translate to? You are seeing the screen, somebody in the class? They drive.
Yellow.
Yellow. You got it very quickly. So O is for they and yet is for drive. Okay, so drive they. It has become drive they. So or maybe they doesn't have anything to do with O. It is simply an influencer. Okay, just like jaunga mein, unga is not really I, but I am the influencer to transform jana to jaunga. Okay, so this phenomenon is called carrying the mark. Jyotsna, please add this slide, carrying the mark. Okay, the word carries the marks of other influencing entities. Okay, so it is possible that O will not be a free morpheme. You will not be able to construct a sentence with O. Okay, they will have a different pronoun for Czech. But coming to the verb, it transforms the word as has been seen. So the basic activity we are carrying out is we are breaking the words into parts or breaking the sentence into tokens and establishing correspondences. So breaking the two sides of the parallel corpus into its parts and establishing correspondences is called alignment. Okay, very fundamental to any machine learning based machine translation activity. So, but Hindi English data will not so easily admit, just like Czech, such a smooth transition. So I carry dhota ho, dhona is to carry. He will carry dhoega. He carries dhota hai. They carry dhote hai. I drive chalata hu. They swim तैरते हैं. Okay, so it will not be so smooth sailing as in Czech. Now I carry or okay, I carry, for example, I carry, he will carry. So this is the Bengali English data. Bengali English data is like Czech. Okay, there are only word forms, and the word forms do not have break between them, unlike Hindi. So dhota hu in Bengali boy. He will carry boy be, and dhoega. He carries dhota hai. Boy is he carries. Okay, so you see languages have different behavior, they have different properties. So then I will carry in Czech was very easy. Po nesu, po for will, u for I, nes for carry. I will carry in Hindi will be मैं ढोऊंगा. So or just ढोऊंगा because the data doesn't have मैं. Now can I construct ढोऊंगा easily? I will carry no. I do not say any data, anything in the training data which will give me unga. I will carry dhounga. But in Czech it was very easy. I will carry sponesu. So I do not see any unga to be obtained from the training data. No. And then they drive had become jedou in Czech. In Hindi, do I get anything from the training data? Drive is chalata. They drive. They carried hote hai. Okay. Then they will drive or they drive. They drive will be चलाते हैं. Maybe I can construct somehow. Okay, so we're running out of time. We can look at the data once again. So this is something very commonly done in language training. Okay, can you really look at the parts of the sentence and like a puzzle, put things together to construct larger entities? Okay, there is something called linguistic Olympiad, just like you have physics Olympiad, maths Olympiad, chemistry Olympiad. There is something called linguistics Olympiad, and linguistics Olympiad typically have these kind of language data situations, and in the competition they ask you to do generalization. Okay, which is almost like a mechanical process, and if you replicate it on a computer, you have a small NLP system there. Okay, I'll stop here and then see if there are any questions.
Why do we use argmax P of E given F instead of argmax P of F given E in statistical machine translation, where E is the source and F is the target? Right.
So PE given F is converted to PE into PF given E. Now, unlike the case of binary classification, in machine translation, PE given F and PF given E, there is not much to choose from between the two. Both the languages are in parallel correspondence. The only difference is that when you're computing through PF given me E and not directly PE given F, you have an additional scoring function in the form of PE, which is called the prior probability. Now, the prior probability is actually language model. You get PE from the probabilities of n-grams. So my favorite example is I like mangoes. If the translation produced is मैं आम पसंद करता हूँ versus मुझे आम पसंद है, then you need a mechanism. Both the sentences are correct, but you need a mechanism to say that मुझे आम पसंद है is better than मैं आम पसंद करता हूँ, because that is idiomatically correct. PE, that PE parameter will ensure that, because language model will give you that score. Okay, so the reason to do apply Bayesian theorem and then do computation is because you get this additional language modeling parameter.